Okay, today, scalar product of two vectors, and let's review a little bit of our definition for work, and this will justify us studying scalar products. We said that work was equal to a force times a displacement times the cosine of the angle between them, and between the two vectors. But let's take a look at something here. I am multiplying two vectors together. That is, force is a vector, displacement is a vector, and this just represents how much angle there is between them. And, well, what is work? What is energy? Okay, well, if I when I laid that banana down there, and if you could calculate how many calories, you could look it up on the internet, right? How many calories of energy are contained in a banana? Would you say this banana has 200 calories to the north? Okay, would that make any sense at all? No. Okay, and all we're doing when we do work is we're transferring energy from one system into another system. So we're just transferring a scalar, or a quantity that is a scalar. We're just transferring it from one system into another system. So work is a scalar. It has no direction associated with it. And this is kind of interesting. We're taking two vectors and we're multiplying them together in this special way, and we get an answer that is a scalar. This has force, has magnitude and direction. Displacement has magnitude and direction, but work only has magnitude. Okay, there's no direction associated with it. Wouldn't make any sense. So therefore, this way of multiplying two vectors together to get a scalar is called the scalar product. Okay, it is something new for some of you, but although this was briefly talked about in AMA, when you did that whole section on vectors, you did talk about the scalar product. But I'm going to teach this as if you've never seen it before. Okay, so anyway, let's abstract from here. We're going to, well, first let me tell you what multiplication is with scalars. Okay, if you're just going to multiply two scalars together, let's say 2 times 3, right? Now, this is your operator. In other words, it's a symbol that represents a set of instructions that tells you what to do with these two quantities. And it just says, hey, we're going to add up 3 2 times. So in other words, we're going to go 3 plus 3. Okay? And then, of course, now we've turned this operator into another operator, the addition operator, which we talked about before. But you just go 1, 2, 3, 4, 5, 6. Okay? Well, what about, 3 times 2? Well, that just says, hey, add up 2 3 times. That's what that means. So you go, okay, 2 plus 2 plus 2, and of course that's also equal to 6. Okay, so, all these years you've been doing this, but really we've got an operator here that tells you what to do with these numbers. Okay, well, now we're going to have a new operator that's going to deal with multiplying vectors together. And remember, vectors are different things than scalars. So if you're going to multiply them together, you need a different set of instructions on what to do. So here is our, let's say here's vector A, and we're going to multiply it by vector B. And now we need a symbol for multiplication. We don't want to use this symbol. We're actually going to use it later for what are called cross products. That is, when you multiply two vectors together and you get a vector as an answer. But for the scalar product, what they use is this big fat dot. like this. So quite often, because of the symbol that we use for the operator, they'll call this the dot product. It's more properly called the scalar product. And by definition, this is what you do. You take the magnitude of A, which I'll just write as A without a vector hat on it, multiply that by the magnitude of B, and then multiply by the cosine of the angle that is between A and B. And so that'll give you the scalar product for those two vectors. Okay. And so look at this is just what we did with work. We wanted how much force are we applying through a displacement. Only the component of the force that's in the same direction as the displacement is transferring any energy over. So that's why we multiply by cosine theta. So the scalar product was invented because we have situations like work where it makes sense. It turns out, though, there are other quantities, vector quantities that we multiply together in this way. Okay, and we'll talk about those as they come up. So this little mathematical pattern that we see here, multiplying the magnitude of vectors together times the cosine of their angle, comes up over and over again. So mathematicians have given it its own special operator and a name. So I'll quite often call it the dot product. Okay, and remember, your answer is a scalar. So it's really kind of nice to call it the scalar product. Well, this is all fine and dandy, and but it can be kind of difficult. I mean, what if I said, all right, A is equal to 10 meters at 30 degrees, and B is equal to 15 meters at 45 degrees. Okay, what is the scalar product of those two? Well, so A dot B in this case is equal to 10 times 15. Okay, so we're going to get a square of some kind here. But what is the angle between them? Remember, that's what this means right here. It's the angle between these two vectors. Or this theta here means the angle between these two vectors. So that would be the cosine of 15 degrees. Right? If I was to draw a picture of it, here would be here would be A. Oh, here would be A, and then B would be like this. Now the cosine of 15 degrees is pretty close to 1, so but not quite. Hey, a what? Oh, I don't think I have a single punch.
I was like, oh, go ask him how you feel today.
A little sore,
pretty good,
but okay. Yeah. Okay, now. But what if these vectors, though, were in 3 dimensions? What if I gave you an x, y, and z component, and I wanted for each, and I wanted to find the scalar product? Or what if I gave you vector A and B in I, J, K form? How would we do that? Well, it turns out to be pretty easy. So let's talk about unit vectors. Okay, so what is, let's talk about individual unit vectors. What is I dot I? That looks like a Motocon, doesn't it, or something? All right. I dot I. Yeah, it's going to be equal to 1. Because what is the magnitude of any unit vector? 1. That's why they call it a unit vector. So this is 1 times 1. And what is the angle between I hat and I hat? This is pretty easy. What's the angle between this and this? Yeah, it's 0 degrees. And what is the cosine of 0 degrees? It's 1. So really what we're doing here is we're multiplying 1 times 1 times 1. And that's equal to 1. So by the same logic, j dot j equals 1 and k dot k equals 1. And this works for fixed unit vectors. Remember, well, with r hat and theta hat, since they're moving around, you have to be careful. But we don't really have to ever deal with that in here. Okay, now, what about I dot j? What's that? Well, it's 1 times the cosine of 90 degrees. So this is equal to 0. And of course, I dot k, by the same reasoning, is equal to 0. And j dot k would be equal to 0. And the order doesn't matter. The commutative property works for dot products. J dot I would be equal to I dot j. That's pretty easy to see. Okay. Well, so what if I had two vectors, A dot B? But let's say A is equal to 3i plus 2j. That's vector A. And then vector B is equal to negative 2i plus 7j. So I'm just making these up as I go along. How would I multiply these together? Well, it is multiplication, so A dot B is equal to 3i plus 2j dotted with negative 2i plus 7j. And this is actually pretty easy. You go, let's just FOIL it, right? We're just going to FOIL 3i dot negative 2i. Okay, well, this is 3 times negative 2 is negative 6. And then we have I dot I. And I dot I is 1. So this is just going to be negative 6. Now we'll do this. 3 times 7 is 21. I dot j. I dotted with j. Then we'll do this one. This is going to be 2 times negative 2 is negative 4. J dot j. And then this last term, am I still on screen? Just about. All right. 2 times 7 is 14. And you have j dot j. Oh, which one? This should be j dot I. Oops. Thank you. Okay. So I dot j, j dot I, thank you, and then j dot j. Well, I dot I is just equal to 1, but this is equal to 0, and this one's equal to 0. So these terms just go away, and we're left with negative 6 plus 14, and that should be equal to 8. So there's my answer, 8. Not 8 in the I hat direction, or j hat, there's no unit vector with this answer. It is a magnitude only. Now notice what I did here. Really, what I did is I went 3 times 2 and 2 times 7, and I added them together. Now, if I get a little more abstract here, and this is going to be boring, sorry, I'm almost done. Let's say vector A, we're just going to call it some magnitude AX plus AY. And then b is just going to be equal to some value, bx plus by. Well, if I multiply these together, taking the scalar product, I have, let's just do it like this. We're going to dot these. Ax dot bx, and then you have I dot I, which is 1. And then let's do this. Ax by, okay, I could write that down, but what have I got? I got I dot j. That's 0. So let's not bother to write it down. That term is 0. Now let's do the second term here. Ay times bx, okay, I could write that down, but I've got a j dot I, which is 0. But here I've got an ay dot by, and I got a j dot j, which is 1. J dot j is 1. And there you go. This is what, so I could say a dot b is equal to ax bx plus ay by. And of course, hey, let's just make this as general as we can. We could extend all this reasoning to the z direction easily enough. AZBZ, which would have been a great title for a band, I think. Okay, AZBZ. Now, by the way, some math books or physics books will actually use this to define the dot product. Okay, but it really doesn't matter what you use to define the dot product. You can use, this one. A dot b, by definition, is AB cosine theta, or you can use this to define the dot product. Either one will work. They're both true. Okay, so yes, foiled again. Now here's how you can use this, though. Let's say I've got 2 vectors. Well, you know what? I'll use the 2 vectors I have right up here because I already know the answer. What if I got room up here. I'll use this part of the paper. Let's say given you have vector A is 3i plus 2j, and vector B is negative 2i plus 7j. And maybe what you're trying to find is theta, where theta is the angle between these 2 vectors. Now, with 2-dimensional vectors, it's pretty easy just to draw a picture of it and, express them in polar coordinates and then just subtract their angles to figure out what the angle is between them. But with a 3-dimensional vector, that becomes much more difficult. But I'll show you a really easy way using dot products. We can say, well, A dot B is equal to A B cosine theta. Oh, solve. Okay. Well, just solve for the angle here. Cosine theta is equal to A dot B over A times B. Now, do you see the difference between this and this? Now, this we already did this down here, A dot B. This turns out to be 8. But we need A times B. Now, what's the magnitude for A? Well, let's take a look at A. 3 squared plus, is 9. 9 plus 4 is, what is it?
Root 13.
So this will be root 13. It's okay to write it as root 13 here, but when you get your final answer, don't write it as an exact number. And then B, here we have 2 squared is 4, and this is 49. So that's 53, right? And then so this is times the square root of 53. So if I want the angle theta, what I need to do is take the inverse cosine of 8 over root 13 times root 53. And what do you get? Somebody's working on that?
72.3 degrees.
72.3 degrees? Okay, I'll take your word for it. I'll just take the inverse cosine of that. So, just by using the definition of the dot product, I can figure out the angle between two vectors. That's what it's used for quite a bit. But it's also used to find work. We're going to be doing a lot of problems with work. We have a force times a displacement, but they're not in the same direction. So we have to take the scalar product to get the answer. Okay, any questions? Okay, that's all. Yes?
Does the displacement have to be in the same direction as the force?
No. To take the scalar product? No. What you do is you take the scalar product. So the question was, does the force have to be in the same direction as the displacement in order to calculate work? Well, what you're going to do, is if you'll have a let's just go back to our example. What if I just rename these variables? Okay. And I said A is force in newtons, and B is displacement in meters. So how much work was done? Well, I would go A dot B, and I would get 8 joules of work. Now that's not very much. I mean, what if they had been in the same direction? You get a lot more. You would have gotten more work. So that's the beauty of it. The two vectors, the force vector and the displacement vector, don't have to be in the same direction to easily calculate how much work is being done by that force. Yes.
If you find A and B to be if you define them in terms of vectors that are not I, J, and K, do you use that FOIL method that you used to?
We're
still work?
We're only going to use in this class. We're only going to use I, J, K to do it, or I'll give it to him in polar coordinates, and you can go magnitude of A times magnitude of B times the cosine of the angle between them.
Would it work though?
Yeah. Well, I don't know.
Okay.
I don't know. Okay, that's it.